Hello. In this video, we're going to look at an application. A mathematics professor found that after introducing his dog Puff to a new brand of food, Puff's weight began to increase. After X weeks on the new food, Puff's weight in pounds was approximately given by W of X equals square root of X plus 40, for 0 is less than or equal to X is less than or equal to 6. Find the rate of change of Puff's weight after X weeks. Now, this doesn't necessarily say instantaneous or average rate of change. If it doesn't say either one, and it only tells us X weeks, it doesn't tell us between 2 weeks, it wants the instantaneous rate of change. In other words, it's wanting the derivative. That's really what this is telling us. Because it doesn't want after a certain number of weeks, it wants to know after every single number of weeks, after every single X weeks. So you don't want to do this an infinite number of times. Well, frankly, you don't have that much time, but you can do it once and you're done. So to do that, that really means we want to find W prime of X. And this is the limit as H goes to 0 of W of X plus H minus W of X and then all over H. Now, W of X plus H would just be the square root of X plus H plus 40. In other words, going up here, that X becomes this entire X plus H. So we're going to replace this with W of X plus H. And this is going to give me the limit as H goes to 0 of the square root of X plus H plus 40, and then subtract off the original square root of X, and then plus 40. All over H. Awesome. Now, here's the thing. This 40 and this 40 cancel because we are subtracting. But I can't take away these two because one's the square root of X plus H, the other is the square root of X. They're not the same radical, so they don't cancel each other. So this just remains the limit as H goes to 0 of the square root of X plus H and then minus square root of X all over H. Awesome. And this should remind you of something that we've seen before. Square root minus a square root. We can actually get rid of the square roots by multiplying by the conjugate. And the conjugate of the numerator is the square root of X plus H plus the square root of X. But if we do that to the numerator, we do that to the denominator. Now the reason that we're doing this is to get rid of this H, and it'll happen just kind of almost a magical way, but it'll happen. So what we're doing is we're taking A plus B and multiplying by A minus B, the conjugate of two binomials, and that gives us the difference of two squares. So this is going to give us the limit as H goes to 0. Square this just leaves us with X plus H, and then subtract off the square of this, and that leaves us with X. In other words, square root of something squared is that something. Then all over H, and then times square root of X plus H, and then plus the square root of X. Awesome. Now notice this X and that X cancel each other. And then notice that you have an H in the numerator and the H in the denominator. Those two cancel as well. So we're left with the limit as H goes to 0 of 1 over square root of X plus H and then plus square root of X. Now if you notice, the H goes to 0 here, we're left with the square root of X plus square root of X, and they're the same radical, so you can add them, combine like terms. So this is going to give us the limit, well, just plug it in. So that's just 1 over square root of X plus square root of X, which is 1 over 2 square roots of X. So this is the rate of change at any given week. The 0th week, well, it's undefined, so it doesn't really matter because that's before they started before Puff started the diet. Put in a 1 here. Square root of 1 is, well, 1. So it leaves us with 1/2. Now, what that means is that it's 1/2 pound per week. Because if we look up here, W is in pounds, H is in weeks. So it's pounds per week. So at x equaling 1, W prime of 1 equals 1/2 and then pounds per week. The second week is 1 over square root of 2 times 2, whatever it worked. But at the 4-week mark, square root of 4 is 2, so it'd be 1/4 pound per week. So the rate of change starts out large, and then it's getting smaller and smaller and smaller over time. Now that's the rate of change. Okay, so it's important for us to keep in mind what the difference is between the rate of change and the actual function itself. So what I want to do is I want to go ahead and stop with the notes, and I want to go ahead and go to the calculator so you can kind of see what's happening. I'll see you there. Okay, welcome to the calculator. Let's go to y equals here. Clear anything in there. Now let's type in the original function, which is the square root of x, and then right arrow to get out there, and then plus 40. Awesome. And then graph. You don't see much. That's because that's for a reason. So I'm going to start with x being 0 for the minimum. For the maximum, let's go 16. For the y minimum, I'm going to say 0, and the y maximum would be 60. Let's see what that looks like. Looks kind of like that. It's a little bit weird. So instead, let's go for the window. Let's actually make the minimum to be 35 and the maximum to be 50. There we go. That's better. So this is the original function. Now, notice that this derivative here at the very beginning is actually technically vertical, but it's actually increasing after 1 week. It's right here. The tangent line looks like that. And I think I can draw that. So second, draw, and then 5 is tangent. Let me go over here to close to x equaling 1. Is that close enough? Yeah, that's close enough. There you go. So that's x equaling 1. Now let's go to x equaling 4. So let's draw the tangent line at x equals 4. Or at least relatively close to it. Ooh, exactly. Awesome. Now notice that x equaling 1, the slope was this. X equaling 2, the slope is this. It's a decreasing slope, but that just means that the function itself is increasing this entire time. But the rate of increase is slowing down over time, so it's not continuously going up. Well, it is continuously going up forever, but how quickly it's going up is reducing. Okay, so let's go over here to say 9. So draw the tangent line at 9. No, let's go to 16. Or 14, that's pretty close. There you go. So notice that this is the tangent line here. Alrighty, so hopefully that will help you understand what is happening with the tangent lines and what is happening with the original function itself. Alrighty, well, I think I'm going to go ahead and end the video here, and I will see you in the next one. Have fun.